Calculus 3. First section is entitled Sequences. Sequences. Suppose you were given a sequence. Say, a sub n is equal to 2 to the n. You were asked to write down the first few terms. Well, the first term is denoted by a sub 1. You have to figure out what it equals. It should equal a real number. A sub 2 is in the second term, a sub 3 is the third term, and so on. A sub n equals 2 to the n is very similar to, say, f of n equals 2 to the n. If you'd rather write f of x equals 2 to the x, it's fine. N and x are called dummy variables. Now, whether you use f of x or f of n, somebody asked you what f of 1 equaled. Instead of n or x, you'd write 2 to the 1 or 2. Somebody asked you, say, what f of 4 equals. Instead of what was inside here, whether it's x or n, you'd write down 4. And of course, that's 16. But this is very similar to what's going on in the left. They're telling you that n is 1. So that n is 1. You get 2 to the 1 or 2. Now n is 2. So you get 2 to the n, but n is 2. Get 4. And then you get 2 to n, which is 3. That's 8. Then you get 2 to this number, which is 4. Okay, whatever n is, you put right there. And how do you know what n is? Well, n is in the lower right-hand corner. Look in the lower right-hand corner next to 8. And you get 2 to the 5. A sub 4 is 16. A sub 5 is 32. That's the first few terms of a sub n. Try a couple more. So instead of n, you put in the number. What number do you put in? The term number. You want to know what a sub 22 is? Plug in 22 for n. If they tell you that a sub n is equal to 5 minus 1 over n plus 1 over n squared. Well, instead of n, you plug in whatever you want n to be. A sub 1, that means you want n to be 1. So wherever you see n in this row, namely here and there, you plug in 1. 5 minus 1 over 1 plus 1 over 1 squared. 1 over 1 is 1. 5 minus 1 is 4. 1 squared is 1. 1 over 1 is 1. 5 minus 1 is still 4, plus that last 1 is 5. What is a sub 2? Well, it's 5 minus 1 over n, but instead of n, I write 2. I'm just reading this, but instead of n, I'm writing 2. Minus 1 over n plus 1 over n squared. So it's 5 minus a half plus a quarter. 2 squared is 4. Think dollars. Think dollars, because then it'll work out. 5 minus half a dollar, $5 minus half a dollar is $4.50. And then you add on a quarter. $4.50 and a quarter. It's $4.75. It's 4 3/4, or 4.75. Okay, a sub n is equal to 5 minus 1 over n plus 1 over n squared. So everything, say, is over 9. Of course, 3 squared is 9 and 3 is 3. The first common multiple is 9. I want to write 5 with a 9 on the bottom. 9 times 5, 45. So 5 is 45 over 9 minus. I want to write 1/3 with a 9 on the bottom. Well, 1/3 is equal to 1/3 times 1. I want to write 1 this way. If you want to change the way something looks, and I do, I want 9 to be in the bottom. That means you multiply by 1. 1 times 3 is 3. In the bottom, 3 times 3 is 9. So we take away 3 over 9. And then we add 1 over 9. 45 minus 3 is 42. Plus 1 more is 43. You can leave the answer like that. Or you can say that, I guess it's 7 ninths. Yes, it's 4 and 7 ninths. That's a sub 3. That's what a sub 3 equals. Instead of n, plug in the values for n. How do you find the value from n? Well, you find a and you look what's in the right-hand corner of a. Like over here, there's my a, lower right-hand corner is 3. That's n. And we can name the sequence other than by the letter a. We can name the sequence b sub n. So then instead of a sub 1, it's just b sub 1. Okay, that shouldn't be a big deal. And you'll see that if you have, say, more than one sequence. If you have 2 sequences, one will be called, say, a sub n, the other one will be defined as b sub n, or named b sub n. It's just a name. If your parents had 2 kids, or if you had 2 kids, you name the first kid one name, and in most cultures, you name the second kid a different name. Let's try one more. A sub n is equal to 3n factorial divided by n minus 1 factorial, or divided by, say, n minus 2 factorial. Now, you can clean this up if you like. You can clean it up, or you can clean it up later. I'll show you what I mean. If you wanted to know what, and they tell you that n is greater than 2. That is, there's no a sub 1, okay? The a sub 2 is, now remember, this is not 3n all factorial. It's not that. It's 3 times n factorial. And n is 2. 2 factorial over n minus 2 in brackets factorial. It's 3 times 2 factorial is just 2 times 1. And 0 factorial, 2 minus 2 is 0. 0 factorial is defined to be 1. So the 1's cancel, you just get 6. A sub 4, for example, would be 3 times n factorial divided by n minus 2 factorial. I just write n that way. Make believe that decades ago, when you learned the alphabet, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. Make believe that's the way N was written. That's the way you write N. In this problem, that's the way you write N. The first step, this first step, I don't want there to be any math involved. Okay, this first step here, there should be no math involved. Okay, so you have 3 times 4 factorial, which is 4 times 3 times 2 times 1, divided by 4 minus 2 is 2. 2 factorial is 2 times 1. And that cancels out. And you get, you're probably weak on your 12 times table, so why not go 3 times 4 is 12? Let's not do that. 3 times 3 is 9. 9 times 4 is 36. So it's 36. Now, what is this that I'm talking about? Maybe we could clean it up first. That is, we can simplify the equation first. Well, n factorial, well, it's n times n minus 1 times n minus 2 times n minus 3 times n minus 4 all the way down to times 3 times 2 times 1. And we have 3 times n factorial. And we're to divide by n minus 2 factorial, which is n minus 2 times n minus 3 all the way down to 3 times 2 times 1. But all of this is going to cancel out. They're the same. That is n minus 2 over n minus 2 reduces to 1, n minus 3 over n minus 3, all the way down to 3 and 2 and 1 canceling. So all we're left with is 3n times n minus 1. We're just left with that. And we can use that rule for a sub n. And again, we're told that n is at least 2. So if you wanted to know a sub 4, it's 3 times 4 times 3 times n, times n minus 1. So it's 3 times 4 times 3, which is 9 times 4, and we get the same answer. So sometimes you may want to simplify first. If you don't want to, don't. Makes the number smaller, but that's up to you. Get the right answer. Now, I'm going to give you a sequence. So, for example, when you had a sub n is equal to 2 to the n, a sub 1 was 2 to the 1 or 2, a sub 2 is 2 squared, which is 4, a sub 3 is 2 cubed. That is, we keep multiplying by 2. So the sequence a sub n is equal to 2. So let me not write a sub n equals. If you have the sequence 2, 4, 6, 8, 10, 12, etc., if you have the sequence, a numbers, that's the sequence, write it down in the shorthand notation. Write an expression for the nth term. And you would say, well, a sub n is 2 to the n. Because that is a sub 1, because it's the first term. And this here is a sub 2, because it's the second term. And this here is a sub 3, etc. Let me give you a sequence, and we're going to write down the rule for the nth term. Suppose you have 1, 4, 7, 10, 11, 13, 16, 19, etc. So we want a sub 1 to be 1, a sub 2 to be 4, a sub 3 to be 7. Well, these numbers are very similar to the 3 times table, because they keep going up by 3. The 3 times table is 3, 6, 9, 12, 15, 17, 20, etc. So again, I want to write the general term for this, the nth term. I want to write a rule for the nth term. Well, the numbers correlate the bottom number. The number on top is always 2 less. the number on top is always 2 less. This here is 3 times 1. The 6 is 3 times 2. The next one is 3 times 3. The next one is 3 times 4, and so on. Well, how do you go from 3 times 1 to get the number right on top? Take away 2. How do you go from 3 times 2 to get 4? Take away 2. The nth term, we multiply 3 by n. And then we take away 2. A sub 1 is 3 times 1 minus 2, which is 3 minus 2, which is 1, which is correct. The first number is 1. It really is. And a sub 2, instead of n, I write 2. 3 times n minus 2 is 6 minus 2 is 4. And what do you know? The second term is 4. A sub 3, 3 times n minus 2 is 9 minus 2, it's 7, which is exactly what the third term is. So here is the answer. The question is, again, write an expression for the nth term of the given sequence. It is find the pattern. You keep adding 3. That is, you're on the 3 times table. But you may have to shift up or down. You might have to add 2 or take away 1 or add 11. You have 2/3, 3/4, 4/5, 5/6, 6/7, etc. Now, let's just look at the numerator. Well, let's notice the denominator is always 1 more than the numerator. So, if we knew the numerator was in the form of 7n plus 83, then the denominator would just be 1 more. The denominators are always 1 more than the numerator. 3 is 1 more than 2. 4 is 1 more than 3. 5 is 1 more than 4. Whatever the top is, if you figure out what the top is, you have the bottom. Now, I want this to be the first term, and that to be the second term, and the third term, and the fourth term, and the fifth term. Well, you know what? Let's just look at the numerators. The first term, the numerator is 1 more than 1, the first term. The second term, the numerator is 1 more than 2. The third term, the numerator is 1 more. In general, whatever the subscript is, the numerator will be 1 more. That is the fifth term. First, second, third, fourth, fifth. Fifth is like 5. The numerator is 1 more. And the denominator is 1 more than that. The denominator is always 2 more than the term number. First term, add 2, get the denominator. 1 plus 2 is 3. The second term, the denominator is 2 more, it's 4. And there's your rule. There's your rule. You have to observe the pattern, which probably isn't that hard in this case, but then you have to be able to write it up in this notation. Your term number. 1, 2, 3, 4. Really, first, second, third, fourth, but think 1, 2, 3, 4. Makes life a bit easier. How about the numerators are 1, 2, 3, and 4, etc. And the denominators are 2 times 3, 3 times 4, 4 times 5, 5 times 6, etc. Well, this is the first term, the second term, a sub 3, this is a sub 4. A sub 3 means the third term. This is a 1, a sub 2, a sub 3, a sub 4. Well, notice that the subscripts always match the numerator. The subscripts always match the numerator. So the nth term. If this is n, then the numerator is n. Now what about the bottoms? When it's the first term, the first factor is 1 more. The second factor is 2 more. When, for the second term, a sub 2, the first number in the bottom is 1 more. The second one is 2 more. A sub 4, the first number on the bottom is 1 more, and then it gets multiplied by 2 more. So if the subscript is n, in the bottom I'm going to have 1 more than n times 2 more than n. And there it is. Okay, you have to recognize the patterns. Not enough just where if somebody says, well, what's the next 2 terms? You say, oh, the numerators are 5 and 6, and the bottom is 6 times 7 and 7 times 8. I mean, that's good, but that's not enough in this case. You do need to see that. You need to see the pattern. But then you have to write the pattern in general. What do I mean by in general? Forget all this above us, above that line. Here's your rule. A sub n equals that. For example, a sub 4. That is, n is 4. So it's n divided by n plus 1 times n plus 2. That is, it's 4 over 5 times 6. The fourth term is this. Exactly what the fourth term should be. So the rule is working like a charm. Okay. How about this one? This one's straightforward. 1 or half or 6 or 24 or 1/128. Well, this is a 1 over 1. How do you go from 1 to 2? You add 1. Then you add 4, and then you add 18. And then you add 96. I don't see a pattern there by adding. I mean, you don't always have to add the same amount. I mean, maybe first you add 3, and then you add 6, and then you add 9. That's a pattern. Then you add 12. You added 3, and then 6, and then 9, and then 12. That would be a pattern. But I don't see a pattern with 1, 4, 18, 96. There might very well be one, but I don't see it. So we don't think adding. Let's think multiplying. What do you multiply 1 by to get 2? The answer is 2. What do you multiply 2 by to get 6? 3. 6 by to get 24? 4. 24 times 5 is 120. This is factorial. 1 factorial is 1. 2 factorial is 2. Now remember, 3 factorial. 3 factorial is 3 times 2 times 1. But that's 2 factorial. So it's 3 times 2 factorial, which I just figured out over here, is 2. And 3 times 2 is 6. That is, 3 factorial is nothing more than 6. Then now 4 factorial is 4 times 3 times 2 times 1, also known as 3 factorial. So it's 4 times 3 factorial, which is 6. So the final answer is 24. 5 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. But that's 4 factorial. So it's 5 times 24, which is 120. And 2, 6, 24, and 120, those are exact, and okay, here. 1, 2, 6, 24, 120, that happens to be exactly the denominators. It's exactly the denominators. You need to see factorials. So what you might want to do is write down the sequence different looking. That is, it's 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial is 1 over 24, 1 over 5 factorial is 1 over 20, and hopefully you see our pattern. They all have 1s on the top. They all have 1s on the top, so in the nth term we'll have 1 on the top. And for the first term, it has a 1 factorial. For the second term, it has a 2 factorial. A 3 factorial for the third term. A 4 factorial for the fourth term. So it's n factorial. And after all, if n is 4, you'll get 1 over 4 factorial. 1, 2, 3, 4. Got it. A sub 2 will be 1 over 2 factorial. 1, 2. Yep, they're the same. So here is your answer. That's an expression for the nth term. It's a rule to get the nth term. What's n? You tell me. The 50th, the 18th. That is, this rule should work for any term number that you want. If you want a sub 22, it's 1 over 22 factorial. Give me the general term. Now we're going to talk about the divergence or convergence of a sequence. We're going to talk about the general term of a sequence. So, before we can talk about whether a sequence converges or diverges, we need to understand what that means. Now, if you have a sequence that, say, is 2, and then 2 minus, maybe we don't have 2. Here, you have 2 minus 1, and then 2 minus a half. 1 is like 1 over 1. 2 minus a half. 2 minus a third. 2 minus a quarter. 2 minus a fifth, etc. So the first term is 2 minus 1, which is 1. The second term is 2 minus a half, 1 and a half. Then you have 2 minus a third, which is 1 and 2/3. And then 2 minus a quarter is 1 and 3/4, and 1 and 4/5. Basically, you're having 2. You have 2. and you take away 1, and then you take away just a half, and then you take away even less from 2, a third, and then you take away less than a third, you take away a quarter, so you have 2 minus an even smaller number, and then 2 minus an even smaller number. Eventually, you'll be at 2 minus 1 over a million, which is very, very close to 2. This sequence is converging to 2. And the sequence, of course, would be 2 minus 1 over, because they all have 2 minus 1. 2 minus 1. 2 minus 1. It's the bottom that changes. In the first term, the bottom is 1. And in the second term, this is the second term, the bottom is 2. And in the third term, the bottom is 3. It's 2 minus 1 over n. This converges to 2. That is, at the end, the last term, whatever that means, because there is no last term. The terms are approaching 2. As you go further and further out into the terms, the millionth term, the 10 billionth term, the trillionth term, you're getting closer and closer to 2. You can get as close to 2 as you want. Just let n be big enough. This is approaching 0. As n gets bigger and bigger and bigger. 1 over a billion. If you had one pizza pie and you cut it into a billion pieces of equal size, and you had one of them, you had 0. You had nothing. You won't even be able to see it, it'll be so small. And that's what's happening, but it'll never be 0. Because I know a fraction is 0 when the top is 0, but our top is always 1. So when it converges, it means what happens at the tail end, all the way to the right. The millionth term, the 10 millionth term, far, far out. What are the terms in there? What are they getting closer and closer to? Possibly they're not getting closer and closer to anything. Then we say it diverges. Okay. A sub n converges, approaches, at the end, approaches 2. It converges, to 2. It converges to 2. Now, another way of looking at it, if you have that sequence, like I said, I want to know what happens far, far out. That is, what happens when n approaches infinity. This is a limit problem. You can think of it as this. Once in a while you'll get burnt thinking of it like this, because here it's continuous. X is approaching 0 through all numbers. Here, n is just integer. N is 1, and then 2, and then 3, and then 4. Excuse me, infinity I meant to write. First, n is 1, and 2, and 3, and 4, and eventually 10 billion, 10 billion and 1, a trillion and 5, 3 trillion, 923 billion, 428,000, 104. But down here, x just doesn't have to be an integer. X can be 23.5 or 23,305,800. It can be the square root of 13,284,000. But usually it'll be okay. And if you remember, 1 divided by really large is 0. So you get 2 minus 0, or 2. Converges to 2. Both of these equal 2. Okay. Now, what happens when a sequence does not converge? There are 2 ways that a sequence cannot converge. That is, diverge. And if you have 1, 2, 3, 4, 5, etc., it's not getting closer and closer to any number far out. It's going to infinity. It's going to infinity. This sequence would be a sub n equals, well, that's the first term, and that's the second term, and that's the third term, and that's the fourth term. An just equals n. And after all, if n was 1, then that's 1. Exactly correct. When n is 2, that is the second term, a2, n is 2. Exactly right. When the third term, n would be 3. The a sub 3 equals what n is, which is 3, which is the third term. Now, if you take the limit of a sub n as n tends to infinity, well, a sub n, the limit as n goes to infinity of a sub n. But that's n. It says so. A sub n equals n. And as n gets bigger and bigger and bigger and bigger, what happens to n? It gets bigger and bigger. It's infinity. We say that a sub n diverges. Now that's one way to diverge. You can also diverge to negative infinity. After all, if it was negative 1, negative 2, negative 3, negative 4, negative 5, it would be negative n. A sub n would be negative n. It would be negative n. And it would converge to negative infinity. Actually, maybe there's two other ways to diverge. Another way to diverge is, say, this way. Suppose you have you have the sequence 1, negative 1, 1, negative 1, 1, negative 1, etc. I know, far, far, far out there, it's going to be 1, negative 1, 1, negative 1. It's not approaching any one number. It's not approaching any one number. It diverges. It only converges if you can guarantee me that it gets closer and closer to a particular number. 2.8, the square root of 17, pi, the number 2, the number 3 over 2, 7, 8, 23,418,000,000. If the terms start getting closer to that really large number I just said, 23,418,000,000, then it converges. Now, a sub n in this case, well, you know that if you raise a negative to an even power, it'll become positive 1. If you raise negative 1 to an even power, and if you multiply negative 1 by itself 2 times, you get 1. This is positive 1. If you multiply it by itself another 2 times, that is 4 times. You get 1 times 1 is 1. Multiply it by itself another 2 times. This will be 1. This is 1, this is 1, this is 1. If you did it 2 more times, that's 1. If you multiply by itself an even number of times, you get 1. Now, every odd number, like 7, is an even number plus 1. 17 is 16 plus 1. 103 is 102 plus 1. If you have an odd number of negative 1s being multiplied, what you can do is get an even number of them, say that's even, and then you're going to have 1 left over. The evens you can pair up. Those two, these two, pair them up in the middle there, and then those two. The product will be positive 1 times negative 1 is negative 1. I want the odd term numbers to be positive 1. I'm going to put n plus 1. If n is 1, 1 plus 1 is 2. A negative 1 to an even power like 2 would be 1. Now, a sub 2. A sub 2, that means n is 2. 2 plus 1 is 3. A negative 1 to an odd power like 3 should give me negative 1. A sub 3, if n is 3, then n plus 1 is 4. Negative 1 to the 4th power is plus 1. That's the nth term, the general term. A sub n is equal to negative 1 raised to the n plus 1. Okay, I mean, think about why you could have also said negative 1 to the n minus 1. N is even, doesn't matter if you add 1 or take away 1, it'll be odd. N is odd, doesn't matter if you add 1 or take away 1, it'll become even. Problem is that it diverges. The limit as n goes to infinity of a sub n, that is, the limit as n goes to infinity of a sub n, which is negative 1 to the n plus 1, this diverges. I don't know what this answer is. It keeps ping-ponging between plus and minus 1. Okay, it keeps ping-ponging between plus and minus 1. Now, just because the signs alternate, that does not mean that it has to diverge. For example, if you have 1 over 1, negative 1 over 2, positive 1 over 3, negative 1 over 4, positive 1 over 5, negative 1 over 6, etc. Well, if we were to draw that, here's 0. First we have 1, and let that be negative 1. We have 1, we have negative a half, we have positive a third, negative a quarter, positive a fifth, negative a sixth, positive a seventh, negative an eighth. They're getting closer and closer to 0. The positive terms, they're getting closer and closer to 0. The negative terms are getting smaller and smaller and smaller and smaller. They're getting close to 0. It's converging to 0. Okay, the a sub n term will be, well, the bottom is just n. The first term has a 1, the second term has a 2, the third term has a 3. The denominator is always the same as the term number. And the numerator is negative 1 to either n or n plus 1. In this case, it's n plus 1. Now, if you take the limit, the top will always be fluctuating between plus and, take the limit as n goes to infinity. The top is going to keep ping-ponging between plus and minus 1. But the bottom is going to 0. Whether you're 1 divided by close to 0, the bottom is going to infinity. If you're plus 1 and you're getting divided by a big, big, big number, or if you're negative 1 and you get divided by a really, really big number, you're getting closer to 0. This diverges to 0. So just because the signs are alternating doesn't mean it can't converge. So basically you want to look at the limit at infinity. You want to look at the limit at infinity. If a sub n is n plus 1 over n, what you can do is take the limit as n goes to infinity of a sub n. That is, the limit as n goes to infinity of n plus 1 over n. Now, this is very similar to the limit as x goes to infinity of x plus 1 over x. And we talked about this in Calc 1. If x is going to infinity, and you have a polynomial in the numerator and a polynomial in the denominator. Go back and look at what polynomial means. If the degrees are the same, and they're both 1, then if the highest degrees are the same, then you just divide the numbers in front, and there's your answer. If the numerator has a higher degree, if the numerator were x to the 4th, and the bottom was x squared, the highest degree on the top was x to the 4th, the highest power on top is x to the 4th, and the highest power in the bottom was less than 4, say 2, then the answer is plus or minus infinity. You'd have to think about if it's positive or negative infinity. If the denominator had the larger power, the highest power in the denominator was higher than the highest power in the numerator, then it goes to 0. This, since the degrees are the same, divide the numbers in front. Okay, there is one way out in this problem if you didn't think that. N over n is 1 plus 1 over n. Okay, 1 plus 1 over n. As n changes, remember limits are really friendly. It's the limit of the first term plus the limit of the second term. As n changes, whether it goes to infinity or 3.9, 1 couldn't care less, it stays 1. Plus, the limit of 1 over n is n goes to infinity. You have 1 and you're dividing it by more and more and more. You get 0. 1 plus 0 is 0. So it converges. It converges. A sub n converges to 1. Okay, so now you're just back to doing limits again. Go back and review your Calc 1 notes on limits. You have a sub n is n squared minus 1 over n plus 1. This diverges. Why? Because the degree of the top is 2. The degree is the highest power of, in this case, n. In the bottom, the highest power is the understood 1. Since the numerator is larger, since the highest degree, that is the highest exponent, that is the degree of the numerator, is larger than the degree of the denominator. The degree of the numerator is the highest exponent of n you see. The degree of the bottom is the highest exponent of n you see in the bottom. Think about it. If n is 10 to the million, okay, well, you square it and you take away 1. In the bottom, you just get 10 to the million. Okay, 10 to the million squared is super, super, super large. Taking away 1 is like a joke. You get 10 to the 2 million. Remember, you multiply the exponents. You get 10 to the 2 million. That is, you have 2 million zeros and then a 1. And then in the bottom, 10 to the million, you just have 1 million zeros and then a 1. The numerator is so much larger than the denominator. It's 10 to the million times as large. It's much larger. This is infinity. The numerator is larger, has a larger degree than the denominator, and when the variable gets bigger and bigger and bigger and bigger, it's going to go to infinity. Some of them you really have to think about. How about this one? A sub n. A sub n is equal to 2 to the 1 over n. Okay, so you want to know what happens when n gets bigger and bigger and bigger and bigger and bigger. And you can say y is equal to 2 to the 1 over n. Now, a sub n you're replacing with y. Now, if you just look immediately at the limit as n goes to infinity of 2 to the 1 over n, you don't know. It looks like it's going to 2 to the 0 or 1, because this goes to the 0. Okay, you might get burnt without one. What you want to do is get the power that has the variable. What you want to do is get the variable out of the power. So you can take ln of both sides. So you get ln of 2 to the 1 over n. But the 1 over n comes out in front. That is ln of y is 1 times ln of 2, which is ln of 2 over n. Now ln of 2 is just a constant. Now I'll take the limit as n goes to infinity of both sides. If your teacher wants you to prove the answer, well then this is what you have to do. Now remember, ln of 2 is a constant. You have a constant, and you're dividing it by more and more and more and more. You're dividing it by 100 gazillion. It's getting closer to 0. 0. Okay, so let's ignore this step right here. We know that this equals this. The limit as n goes to infinity of ln of y equals 0. Now, won't prove this, but ln of y means log base e of y equals 0. This says e to the 0 equals y. E to the 0 is equal to y. But e to the 0 is 1. This says that the limit as n goes to infinity. Basically what I said we won't prove is the following. You could put the base e in. So e to the ln of y is just y. Go back to your notes. And e to the 0 is 1. So the limit as n approaches infinity of y, which from the very beginning was 2 to the 1 over n, that equals 1. You have this theorem that says log base anything well, that's not true. Here. It says this is x. A raised to the log base a of anything is that anything. If this base and this base are the same, you just get back x. You just get back x. Okay, go back and review your log rules. Okay, this is Calc 3. So sometimes you have to do clever things to figure this stuff out. One more. A sub n is n times the sine of 1 over n. So again, we want to take the limit as n goes to infinity of n times sine 1 over n. Times. Like I said, limits are very friendly. you can take the limit of the first, which is infinity, times the limit of the second. Well, 1 over n is going to 0. And the sign of 0 is 0. So now you have 0 times infinity, or infinity times 0. This is a L'Hopital's rule. Or is it? Or it doesn't need to be. Instead of multiplying by n, instead of multiplying by n, which is n over 1, instead of multiplying by n over 1, you can divide by the reciprocal. After all, if somebody asked you to simplify this, you would say, you know what? Instead of dividing by 1 over n, I'm going to multiply by the reciprocal, which is exactly what we had from the beginning. I just did it in the reverse. Now, at this point, you can use L'Hopital's rule. Or you can remember this from Calc 1. This was the big limit fact in Calc 1. If you have the sign of anything, and you divide by that same anything, and that anything is approaching 0, you're in business. That's anything, and that's the same anything. So we have the first criteria. These both had to be the same. And as the anything approaches 0, these things need to approach 0. X needs to approach 0. And anything needs to approach 0. Well, when does 1 over n approach 0? When n goes to infinity. When n goes to infinity. If n approaches infinity, if that, then 1 over n approaches 0. This statement, n goes to infinity, is the same as saying 1 over n goes to 0. And then I just change the variables. Instead of 1 over n, I'll call it x. Call it x. X goes to 0. 1 over n is x. 1 over n is x. This limit is 1. This limit is 1. A sub n converges to 1. Okay, you have to remember your Calc 1 limits. It's coming back to haunt you again. Problem is, this isn't Calc 1. I'm not going to do a whole lecture again on limits. Okay, there's a very important theorem. The theorem states the following. If our sequence A sub n is bounded, that is, it doesn't go off to infinity. It's bounded. It's between -10, every term is between -10 and 200, or between -50 billion and 103 million. It's bounded. It's between 2 and 4. If our sequence is bounded and monotonic, that means it's always increasing or level. It goes up, maybe it's the same. It goes up, it's the same. It doesn't go up and down. It could go down and be the same, go down and be the same, go down and be the same, but it can't go up and down. Those are monotonic. The terms, one term to the next, either there was no change or it always went up from one term to the next. Or from one term to the next, it stayed the same or it decreased? 1, 1, 3, 4, 5, 5, 5, 6, 7, 8, 9, 9, 10. That's increasing, but sometimes it's the same. So it's not said to be strictly increasing. It's said to be monotonically increasing, non-decreasing. It's monotonic. Or it could have been the reverse way. Imagine if I wrote it down backwards. The numbers are getting smaller or they stay the same. That's what monotonic means. So if you can show that the nth term is always greater than or equal to the n plus first term, then you're monotonic. These greater than or equal. Either they're equal or it's greater. If this is true, then A sub n converges. And you're definitely going to come up against problems that ask, show that this sequence converges. Okay, so now, suppose you have A sub n is equal to 5 plus 1 over n. The problem says, using this theorem, show that it converges. Well, since n is 1 and 2 and 3 and 4, 1 over n is positive. The smallest term, well, what is it bounded by? What is it bounded by? Let us have it. Well, first you have 5 plus 1, then you have 1 over 1, 5 plus 1, 5 plus a half, 5 plus a third, 5 plus a quarter, etc. 1 over 1 is 1. So you have 6, 5 plus a half is 5 and a half, 5 plus a third is 5 and a third, 5 plus a quarter, 5 plus a fifth, 5 plus a sixth, and so on. It's going to be bigger than 5, but less than or equal to 6. A sub n's are all bigger than 5. Why? Because like I said, you have 5 and you're adding something. They're all bigger than 5. And they're less than or equal to 6. Okay? Right. So it's bounded. The sequence is bounded. Now we have to show that it's monotonic. We have to show that it's monotonic. We have to show that one term is always greater than or equal. Every term is either greater than or equal to the next term, or it's smaller than or equal to the next term. Well, A sub n plus 1, that's the subscript. That's what goes in the bottom. I'm adding less, aren't I? I'm adding less. This term, A sub n plus 1, is smaller. Okay, that is. One way to do it is to subtract and show that it's always positive, or show that it's always negative, or equal to 0. Okay, if you subtract the two and you get a positive value, that means A sub n was always bigger. If you get a negative value, that means A n minus 1 was bigger. Or maybe you get 0, which is okay. Well, A sub n is 5 plus 1 over n minus A sub n plus 1 is this. And I think you're okay with 5 minus 5 canceling out. So we get 1 over n plus I meant to say minus 1 over n plus 1. Getting common denominators, which is n times n plus 1, you multiply top and bottom here by n plus 1. When you multiply the 1 by n plus 1, you get n plus 1, minus, over here, you multiply by n over n. 1 times n is n. And n, take away n vanishes, so you get 1 over n, which is a positive number. It's 1 or above, times another positive number. This is positive. The difference is always positive. That means this number is always bigger than this number. That means it's monotonic. In fact, it's strictly increasing. Monotonic means either it's increasing or equal, no change, that is, or the terms are getting smaller, and sometimes one term after another are equal. But other than being equal, it has to get smaller. It can get bigger and smaller. The terms can get bigger, and then level, and then bigger and bigger, and then smaller, and then level. No, that's not monotonic. Either you're always going up or being level, that's monotonic. You could always be going down or being level. That's monotonic. But you can't be going up and going down. Okay, this function is strictly decreasing because the preceding term is always bigger. This is 7, this is 3. 7 minus 3 gave us a positive answer. So we now know it converges. We don't know what it converges to. Okay, the monotonic convergence theorem does not tell you what you converge to, which is unfortunate. It doesn't tell you what you converge to. Sometimes it's very, very hard to tell what it converges to. Okay? I suspect that there are problems out there where mathematicians have not figured out yet what the sequence converges to. But they all know it converges because it passed the monotonic converging test theorem. Okay, let's try one more. A sub n is 4 plus 1 over 2 to the n. Show that this converges by using its theorem. Well, okay. So, when n is 1, this is a half. So you get 4 plus a half. And then when n is 2, you get 4 plus a quarter. And then when n is 3, you get 2/3, 2 to the 3 in the bottom, which is an eighth. And then a 16th. That is, 4 plus a half is just 4 and a half. 4 plus a quarter is just 4 and a quarter. 4 plus an eighth. Now, the thing is, the biggest term is 4 and a half. I mean, you want to say 5, fine. You can say A sub n's are all smaller than 5. And you know what? They're all bigger than 1. This is a positive number. 4 plus a positive number, shucks, that's at least 4. That's more than 4. They're all less than 5. The denominator here is always bigger than the numerator. That is, I know I'm not even adding 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. The denominator is always smaller. That is, this is less than 1. So this is less than 4 plus 1 or 5. Okay, so we argue that it's bounded. It's bounded. Now, is it monotonic? Is it monotonic? Well, what's a sub n plus 1? A sub n plus 1. Instead of n, we put n plus 1. Instead of n, we put n plus 1. So let's subtract the 2. Let's subtract the 2. A sub n minus a sub n plus 1. It's 4 plus 1 over 2 to the n. All of that, take away all of 4 plus 1 over 2 to the n plus 1. Well, 4 minus 4 clearly cancels. So we have 1 over 2 to the n minus 1 over 2 to the n plus 1. Now, if you take 2 to the n, you multiply it by 2, which is 2 to the 1, you get 2 to the n plus 1. That is, if I multiply by 1 as 2 over 2, I'll have 2 to the n plus 1. This is 2 to the n plus 1, and that fraction also has 2 to the n plus 1. So we subtract the numerators. 1 times 2 is 2, minus 1. It's 1 over 2 to the n plus 1. But n is at least 1. N is 1, 2, 3. 2 to a positive number is positive. In fact, 2 to a negative number is positive. The numerator is positive. The bottom is positive. This is always positive. That is, this a sub n is always, always, always bigger than this. All I'm saying is this. If x minus y is bigger than 0, I'm saying that x is bigger than y. How do I know that? Just add y to both sides. X is bigger than y. I call this x and that y. If you subtract two things, then you get bigger than 0. The first thing was bigger. If a sub n minus a sub n plus 1 is bigger than 0, add a sub n to both sides. On the left side it cancels out. On the right side, 0 plus a sub n plus 1 is a sub n plus 1. A sub n is always bigger than a sub n plus 1. A sub 5 is bigger than a sub 6. A sub 7 is bigger than a sub 8. A sub 8 is bigger than a sub 9. Where am I getting this from? I'm letting n be 8. Both of these n's are 8. And please, 8 plus 1 is 9. So the left says a sub 8 is bigger than a sub 9. Okay, that means the terms are getting smaller. Okay, the terms are getting smaller and smaller and smaller. That's what we had to show. We had to show that it was bounded and monotonic. Now I can guarantee you that this converges. It converges. Now, for example, what if you have the sequence negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1? Well, call this a sub n. Clearly, a sub n is in between negative 10 and 13. Every number in here is in between negative 10 and 13. I mean, you could have said negative 2 and 4. You can say negative 3 and 1.5. Negative 1.1 and 1.1. They're all between. They're bounded. This implies a sub n is bounded. Now I have to show that it is monotonic. Remember, this is a sub 1, this is a sub 2, this is a sub 3, this is a sub 4. Well, a sub 1, which is 1, is less than a sub 2. Now, for it to be monotonic, from here on, it must be the case that a sub 2 is less than or equal to a sub 3, which is less than or equal to a sub 4, which is less than or equal to a sub 5. That is, the terms are getting all bigger. But that's not true. We know this is true, but when it comes to A2 and A3, That's A2 and that's A3. 1, negative 1. A sub 2, which is 1, is bigger than A sub 3. It changed. Okay, I mean, here's A1. A2 is bigger, and now A3 is smaller. It's not either always getting bigger or level, or always getting smaller or be level. It went up and it went down. It failed this test. This diverges by the monotonic convergence sequence, or theorem, excuse me. It diverges. Okay, this here tells me A sub n diverges. I suspect again there are possibly, this one I'm less sure of. There may be some sequences that we can't tell what it diverges to. Remember, sometimes it diverges to infinity, sometimes it diverges to negative infinity, sometimes it converges to nothing. Okay? I guess we can always tell if we know it diverges, we can tell if it diverges to infinity or negative infinity. And if it doesn't, then it's something like that one. Okay, that completes their top figure sequences. Good luck.